Okay, thank you. Welcome back. The last session of COVID-5. This is an interesting session from all disciplines. First, as usual, we don't have, I think, new participants, but still, let me remind that the session is session will be live streamed over YouTube. Okay, and you can ask questions through the chat box, and if we have followers in YouTube, they can also write their questions. I hope that we will receive them. In this last session, we have 2 invited and 1 contributed talk. For invited talks, we will have 25 minutes for presentation and 5 minutes for questions and answers. Around 20 minutes, about 20 minutes, I will remind the speaker the time. And so in this session, we have a large spectrum extending from magic states, quantum computation, to quantum radar, to QED waveguides, and from different disciplines. Our speakers from math, from engineering, EE, and to applied physics. So let's start. Our first speaker is Cihan Okay from Bilkent University, from Department of Mathematics. Cihan Hocam, you can share your screen with us, and
okay,
we can start our.
Right, so I think it should be visible. Right,
fine.
Sounds good. Okay, so thank you very much for the invitation. It's a great pleasure to be speaking here. So I'll tell you about a hidden variable model that's discovered recently for universal quantum computation, and that is specifically for qubits. And this is a joint work with Michael Zurel and Robert Rosendorf. So you can find our paper online. It's available, both the preprint and the original paper itself. So today I'll be telling you, I'll be focusing on a specific question, which is an important question among quantum computing people. So what are the essential quantum resources that provide speed up for quantum computation over classical computation? This is a very important problem. So the quantum resources are certain physical features in quantum theory that give you computational speed up when you compare it to a classical computer. So there are a couple of candidates for those resources, but I will be focusing on 2 of them. So first of all, quantum contextuality. So just to briefly say what it is. So this is a notion from quantum foundations, and it has been discovered by Koshan, Specker, and Bell. I'm not going to talk about it too much, so it will be just a parallel notion, but our main focus is going to be the second resource, which is quasi-probability representations, and the Wigner function, which is very famous in quantum optics, as far as I know, is going to play a specific role here. But our goal is to generalize, come up with different kinds of quasi-probability representations. The reason is that in the case of odd dimensional systems, meaning that your Hilbert space has odd dimensions, then these 2 resources are closely related. They actually characterize the computational power in the same way, and the whole picture, as I describe, you will see when I describe it, is going to break down for qubits. So the whole talk, this research project, is motivated by extending those results to qubit, coming up with new kinds of ways of representing quantum states, and also it brings up new kind of phenomenology into the picture, as well as new kind of mathematics. So, well, today's talk is going to be about hidden variable model, and there are certain mathematical objects involved. So there will be a convex polytope, which is bounded. It will have finitely many vertices, and it is going to contain all the quantum states. in other words, all the density operators. So when you have a single qubit, you should keep the following picture in mind. So we have the Bloch sphere here, which is the space of states for a single qubit, and the pure states is a continuum in this case. This is a Bloch sphere, so it's a two-dimensional sphere, has an infinite number of states in it. So the polytope that we describe is going to replace this state space with a larger state space, and this state space is going to have a finite number of extreme points. So these are the vertices. The polytope in the single qubit case is going to be a cube. So we have these 8 vertices giving us the extreme state. So when you choose a quantum state, which is inside the Bloch sphere, naturally, because the mixed states are going to fall inside this sphere, it is going to induce a probability distribution on the set of vertices. Using that probability distribution, you can actually classically simulate quantum computation. So I'm not going to explain precisely how the simulation works, but the picture you should keep in mind throughout the talk is the picture on the right-hand side. So the vertices are going to move to different vertices as you execute your computation. And here I'm going to talk about quantum computation with magic state. So you can think of it in this framework. The computation is implemented by a sequence of measurements. So as you apply your measurements, all you have to figure out where to go. So how to update your vertex. The initial probability distribution given by the quantum state is going to be used for sampling to start the algorithm. So these two pictures are going to be important, but of course, our construction works for any arbitrary number of qubits. So the Gottesman-Lie theorem is a fundamental result in the context of quantum computing. So just to give you an idea how quantum computing works, so you have an initial state, and the unitary transformation is being applied to the initial state, and then you apply a sequence of measurements. So here the wires correspond to qubits, and the input state and the output, the measurement, they're all in the computational basis. So the Gottesman-Lie theorem says the following. So there are 3 components here: the state, the transformation, and the measurement. So if you restrict your set of these 3 components into a subtheory of quantum theory, which is known as the stabilizer subtheory, then the circuit is going to be efficiently classically simulated. So you can find a classical circuit which actually does the same job, so you don't really gain any, efficiently does the same job, so you don't really gain any computational power. So here I'm going to, next I'm going to describe these 3 components in a closer way. And the key object here is the Pauli group, or the Pauli operators. So Pauli operators, they are acting on a Hilbert space which has this specific form. So here we have the n-fold tensor product of Cp. So each copy of Cp corresponds to a wire in this circuit picture. And P here can be 2, which gives us the usual qubit picture, or it can be odd. And the computational basis is going to be consist of n tuples of elements from integers z mod p, integers mod p. When p is equal to 2, Pauli operators have a very, well, it's easier to describe the Pauli operators in the p is equal to 2 case, because everyone's familiar with the these 2x2 Pauli matrices x, y, z, and the first one is the identity. So Pauli operators in the n-qubit case, it's going to be n-fold tensor product of these 2x2 matrices. So of course you can generalize this these operators to arbitrary p, but I'm not going to go into the construction. But there's a way to talk about these operators in the general case as well. So the stabilizer subtheory, remember that it consists of 3 parts. So first of all, the set of observables, or you can think of it as the set of measurements, they are coming from the Pauli group. So Pauli group is a finite subgroup of the unitary group generated by those kind of special operators called Pauli operators, as I described in the previous slide. This is a finite group. So you're replacing the whole unitary group with a finite group in the case of observables. The Clifford unitaries are the normalizers of the Pauli group inside the unitary group. So these are the unitaries when you apply to a Pauli group, when you conjugate a Pauli group, you still obtain another Pauli operator. You still obtain another Pauli operator. So this is also a finite group. So the set of transformations, which was unitary, this is a continuum, now again replaced by something finite. In the case of qubits, the Pauli group, the Clifford group has specific generators which can be easily described. So you have the Hadamard gate, a single qubit gate, the S gate, again, another single qubit gate, and the CNOT gate. This is a 2-qubit unitary, or in the context of computations, they're called gates. So the states of the system, the pure states, think of them as the extreme points of your state, the states of the stabilizer theory. So they are given by the following set. So you take the computational, one of the computational basis vectors. So this is a pure state. Here I'm just taking the n tuple of 0, so that's a natural choice. And then you apply by the Clifford unitaries on the set. So you obtain another finite set of states. So as you see, all three components of the subtheory is finite. But as the Gottesman-Nil theorem says us, we lose computational power if you restrict to these kind of objects. But they are very easy to control. That's kind of the point. So in the context of quantum computation with magic state, it is a computational scheme which is slightly different than the circuit model. You can extend the Gottesman-Nil theorem in the case of odd primes to a larger state space. So instead of considering stabilizer states, you can actually extend the Gottesman-Nil theorem to a larger set of states and then still get efficient classical simulation. So let me first describe quantum computation with magic states. So the formula is as follows. So you start from the stabilizer subtheory, which we know can be efficiently classically simulated by Gottesman-Nil theorem. So to be able to reach quantum universality, you need to include something, and that thing you include is called a magic state. So this is an extra quantum state that does not lie inside the stabilizer state. So quantum universality can be achieved by these three gates. So the Hadamard, CNOT, and the T gate. So the T gate here is the special one because the other two lies inside the stabilizer subtheory, so I can implement them easily, but the T gate is supposed to be implemented using the magic state. So the magic state, a typical magic state is given in the diagram here in the circuit. So if you use that state, this magic state, you can implement on any quantum state beside the T gate. So if you look at the circuit in the middle of the circuit, we see a CNOT, a Z measurement, and a computational measurement in the computational basis, and an S gate. So all of these three components lies inside the stabilizer subtheory. So the using this circuit plus this magic state, we can implement the T gate. So that means we can achieve universality by inputting this extra state into the stabilizer subtheory. So in the quantum computation with magic state, we are not going to think in terms of circuit, but we are going to replace circuit by a sequence of measurements on an initial magic state. It is kind of similar to measurement-based quantum computation, but I'm not going to give too much of details. Just think of a magic state that you start with, or an n-fold tensor product of a magic state, and then you start executing your measurements, which are all Pauli type measurements, or measurements in the stabilizer theory. So what is this theorem that extends Gottesman-Nil theorem? So it's a theorem due to Veitch et al. It says that quantum computation with magic states can have quantum speedup only if the Wigner function is of the magic state is negative. So if you just read this statement in the opposite way, if the Wigner function is positive, that is the specific quasi-probability distribution used here, it's a discrete Wigner function, then if you use it quantum state as an initial quantum state, then it can be efficiently classically simulated. That is, in particular, these kind of states contain the stabilizer state, so that gives you the Gottesman-Nil theorem, but you can have a larger set of states still being efficiently classically simulated. But all of this story happens for odd local dimension, meaning that when the prime p is odd. So to give you a bit more idea on the Wigner function and why this odd dimensional simulation works, so the Wigner function is a Wigner function is is a quasi-probability distribution on this set, or you can think of it as an abelian group, which is Z mod P to power 2n. So this is called the phase space, or this is a symplectic vector space in general. And you can see this as the Pauli group up to scalars. So there are different ways of thinking about this phase space here. So the Wigner function is a quasi-probability distribution, meaning that it can take negative values in general. So when P is odd, we have these two special properties. If you take a Clifford unitary and look at the Wigner function associated to this state, which is given by the conjugation of rho with u, this Wigner function can be obtained from the original one by applying a linear transformation to the phase space. So this is essentially a symplectic transformation, but it's enough to know it's just a linear transformation, so you can actually easily obtain the new Wigner function. So this is important. This is called Clifford covariance. And the other property is that positivity preservation. So if you start from a Wigner function which is positive, and then you apply a Pauli measurement, which is represented by a projector, this Wigner function remains to be positive. So this is also very important. It allows you to run the simulation algorithm. So you start from a positive Wigner function, you sample, and then you start measurements, but the Wigner function stays positive, so you can iterate this process of simulation. So these two are very key properties, but these properties doesn't hold for qubits. So you have to come up with a new idea. So there's an important connection to here, quantum contextuality. So this is a notion, as I said, from quantum foundations. I'm not going to have time to define it, but it actually gives you a good hint why all of this story actually breaks down in the qubit case. So still thinking in the odd dimensional case, there's a theorem due to Howard et al. So which says that quantum contextuality is a necessary resource for universal quantum computation. So again, in the scheme of quantum computation with magic state, the initial quantum state that you start with, if you want to gain some computational power, it has to be a contextual state. So in the other ways, if you want to relate it to quasi-probability representation, which is the Wigner function in our case, the Wigner function serves as a non-contextual hidden variable model if it is positive. So if it is a probability distribution, you can actually describe your state in a classical way. If you want to make it more precise, it gives you a non-contextual hidden variable model. So the idea here is that these two approaches, these two perspectives align perfectly. But if you move to qubits, quantum contextuality side breaks immediately, because in the case of qubits, we have state-independent contextuality. So every state is contextual because of this construction due to Mermin and Perez. So I'm not going to go through this example. The reason I put it here is to show that it is really minimal. It's really small, and then it proves that every quantum state in qubits, for the case of qubits, is actually contextual. So I'm thinking of qubits, multiple qubits. So it's a single qubit is not really important in the story. So the contextuality side breaks down, and it also affects the quasi-probability representation side. As I said, the Wigner function doesn't have these two nice properties that I described for the odd dimensional case. So how are we going to overcome these difficulties? So our solution is to introduce a polytope whose definition is intrinsic to the Pauli group. So it consists of Hermitian matrices of trace 1, such that when you trace this Hermitian operator X with any stabilizer state, these pure stabilizer state, it is non-negative. So these conditions give you a convex bounded polytope which lives inside the space of Hermitian matrices. So in the case of a single qubit, your Hermitian matrices of trace 1 is going to be a three-dimensional real Euclidean space. And then the polytope just turns out to be a cube. So this is the really nice, simple picture. But if you move to the next state, which is 2 qubits, the number of vertices is going to dramatically increase. So you're going to have number of vertices of the order of 22,000. If you move to 3 qubits, the number of vertices is going to jump to a couple million. So for those ones, we don't really have any mathematical, we cannot really handle those cases analytically, but the only thing we know about them is numerical. If you just increase the n, we have no idea. So the number of vertices, so the vertices are going to be denoted by this Vn, and this is going to be our new phase space in the qubit case. So our theorem is as follows. So there are three parts of the theorem. First of all, the first one says that any quantum state can be expressed as a probability distribution. So recall, note that quasi-probability distributions turn into probability distributions. So there's no negativity in the description of states. So the second part of the theorem tells us how to update the vertices when you do a measurement. So the update of the vertices are determined by a probability distribution again. The crucial property is that when you combine these two probability distributions, you recover the Born rule. So the left-hand side is quantum mechanical, right-hand side is purely classical. And this theorem gives rise to a new classical simulation algorithm for the scheme of quantum computation with magic states. Of course, the whole point of this discussion, the keyword is efficiency. So we have seen that in the odd case, the Wigner function serves for certain states, gives us an efficient simulation. So just to give you a little bit detail and connected to the vertices, the Wigner function is defined using a collection of operators, operator basis for the Hermitian space of Hermitian matrices. They are called point operators. So for each element in the phase space, there is a vertex corresponding to. But it doesn't really span the whole vertices of the polytope that we have considered. It only just corresponds to a small part. And if you are able to express your quantum state as a probabilistic mixture of these vertices, then the Weich's theorem tells us that it is efficiently classically simulatable. So for the qubit case, there's a corresponding kind of vertices, but the description of these vertices is much more complicated. So you have to look at, you have to define special subsets of the of this abelian group, which is again Z mod 2 to power 2n. You can think of it as the quotient of the Pauli group after scalars. And non-contextuality plays a natural role in the description of these subspaces. Then, similar to the odd case, if you're able to express your quantum state as a probabilistic mixture, and the probability distribution can be efficiently sampled from, then you can classically simulate your computation in an efficient way. So these are
5 minutes.
Okay, thank you.
Yeah.
So these are the vertices in the first in the odd case and this new in the qubit case. These are not spanning all the vertices of the polytope. So we are only looking at subparts, a few of the vertices in this large polytope. So this construction gives rise to new questions. So we don't know the region of efficiency in terms of which vertices actually give you efficient simulation. So in our latest work, we have been able to extend this region further. So these special subsets, so now we are focused on the qubit case. These CNC vertices, which are of the first type, they have special properties. So for example, their coordinates in the Pauli basis, they are just correspond to these special values that you see, just plus, minus 1 and 0. So these vertices have integral coefficients. When you move to more complicated vertices, you start seeing these rational numbers appearing in these are expectations, by the way. So they start to appear, and then you have more complicated structure. So the picture here shows you the combinatorics behind understanding of these vertices. So these new kind of vertices heavily rely on the structure of abelian subgroups of the Pauli group. So this is a picture of the abelian subgroups of the Pauli group. So it requires a lot of combinatorics here. Mostly graph theoretic ideas to be able to handle these vertices. So, so to conclude, there are two kinds of problems. So the first one is mathematical and the second one is physical. So the first one is about the structure of the polytope. So it's an open problem to find the largest subpolytope which gives efficient classical simulation. So we have seen that it's possible to extend this region, but the understanding and the classification of the vertices of the polytopes in general is unknown. So this is a very mathematical problem to understand the vertices of the polytope and understand how to update the vertices under measurements. So the second part that gives us another kind of question is that negativity in the Wigner function, we have seen it as a resource. So it gave quantum computational power in the odd case, but in the qubit case, this negativity completely disappeared. So it remains to understand the physical properties that determine the efficiency of the classical simulation, hence computational power in quantum computers. So there are two kinds of questions that are begging for answers. And so with this, I would like to end my talk. And here, by the way, I just want to make an advertisement. So I'm hiring postdocs. So if you're interested in these kind of topics, please visit my website so you can find the link there. Okay, thank you very much for your attention.
Thank you. Thank you very much. I'm checking the chat box, but also I think if Fatih has raised his hand. Was this for a question?
I was just clapping.
Okay. Then I want to ask a question first. This is there a recipe to find this classical simulation? I am asking this because just after I posted this so-called quantum permutation algorithm on arXiv, I received an email from Joel Wollman, that's one of the co-authors of 2014 article. He was saying that the speed up is not quantum mechanical, I think, because Wigner function corresponding to all these gates are non-negative. Then the question is, what is the classical simulation? No one found until recently, last year and the year before. There are now classical light simulations, and also mechanical simulations of the algorithm. But before finding them, is there a way? Is there a constructive way how to find them? If you have positive Wigner function.
Yeah, so the algorithm, the simulation algorithm is fixed. For example, in the case of our theorem, and also in the case of Wade's theorem, there's a fixed algorithm. So once you have a positive Wigner function in the odd dimensional case, you can, so there's a fixed algorithm. So yeah, so the algorithm runs as follows. So if you have a QCM, which consists of an initial quantum state and a sequence of measurements, a finite sequence of Pauli measurements. So the way you simulate this is as follows. So you start from your Wigner function. So it's a probability distribution on the phase space. So you sample from there. You start to you choose you obtain a phase point element, right? And then for each measurement, you also know how to update this phase point element. And the update rules in the odd dimensional case is actually given by these two rules. So let's focus on only the measurements. You can also talk about Clifford unitaries, but in the measurements, you know how the phase points are updated. So here I don't have the formula how to do that, but there's a very very explicit way of updating the vertices in the consecutive measurements. So in our case, the two probabilities here, the first one is the initial probability distribution, which you sample from when you start. And these Q probabilities are the ones which corresponds to the measurements. So these two components gives you a specific algorithm. In the odd dimensional case, it works if the Wigner function is positive. In the qubit case here, the algorithm works for any quantum state. Mm-hmm. because we can always, for any quantum state, there is a probability distribution on this phase space. So the point here is that to be able to escape from state-independent contextuality, you need to extend your phase space. So the Vn here is much larger because corresponds to the vertices of the polytope. It's much larger in size than the phase space that is used in the odd dimensional case. So you have to have a very large set of elements here in your phase space. And then the second thing here, for each vertex, you can apply a measurement, and then you can figure out the probability distribution again on the set of vertices. So these two, once you know them, you can just execute your algorithm. In a similar way, the structure of the algorithm, the way you execute it is similar to Waite's algorithm. Here, the difference is that the initial probability distribution and the way you update this probability distribution at each step.
Okay, thank you very much. I'm checking the chat box if there are other questions, because otherwise I can ask one more. I'm trying to figure out your probabilities, the connection between them and these d-squared probabilities that we have in SIG-POEVMs. You know, they exist. In principle, you can formulate everything without any reference to density matrix in terms of these probabilities, as in case of quantum Bayesianism. And they satisfy some equations. There are restrictions. We have polytopes for these pure states. Are they the same? I mean, let me ask in the following way: in d-dimensional space, how many probability values do you need in this approach?
Okay, I mean, a priori, you would need a huge number of. So I mean, a priori, you just have a probability distribution on the set of vertices, and I said the number of vertices goes as in the single qubit is 8. In the next case is 22,000 approximately, and then it goes to millions, and then it grows really exponentially fast. But for a specific quantum state, let's say you're interested in a specific quantum state that you want to simulate because you know it's already a magic state, then you can actually shrink the number of vertices using some theorems from convex geometry. So you don't really need to use all the vertices. You can shrink to a smaller number of part of the set of vertices here. And the connection to cubism here is, again, they are trying to represent quantum states positively. But the problem there, in those kind of arguments, usually the quasi-probability representations, they come from an operator basis. And if you consider only operator basis in the qubit case, you fail dramatically because you can represent the quantum states positively, but then you lose positive representation in the measurements. So the operations cannot be represented positively. And this, the main point here is that you can represent positively everything, both the quantum states and the operations, quantum operations. So that is the main point here.
Okay, I see now. Thank you very much.
Okay, thank you.
Okay, then I think we can thank Cihan Hoca once more and pass to our next speaker. Thank you.
Thank you very much.
Yeah. Well, our next speaker is Ahmet Salmanoglu. I would read it Ahmet Salmanoğlu. I'm sure that our colleagues pronounce in this way. Welcome, Ahmet. So you can share your screen, I think.
Yes,
okay.
If you let me, I am trying to share the screen with you. Okay. I think, yeah.
Okay, so it's 20 minutes. I will just remind you that you have 5 minutes left, okay? And
okay.
people can ask their questions through chat box as usual. So Ahmet Salmanoğlu from Çankaya University will talk about an interesting proposal, an interesting subject from many points of view, which is quantum radar. Okay, thank you.
Thank you. Thank you for your introduction. I appreciate that. And okay, the design of quantum radar from quantum theory to an operational point. Our presentation contained 2 different sections. Part 1, a general schematic for quantum theory and using the quantum theory to model quantum radar. And part 2, in part 2, we discuss about the conceptual design of a quantum radar, and I think it will be very interesting for you. Okay, let's start with part 1. And quantum radar and can be defined as a kind of measurement system like a classical radar. It is because the quantum radar using the microwave photons, but moreover utilize another factors such as quantum phenomenon factors such as entanglement to improve and enhance the target detection and recognition performance. A simple definition about the quantum entanglement. Okay, let's start on our idea, our new idea, the optoelectronic based quantum radar. As you can see here in this section, we replace the traditional electro-optomechanical system with our new design. I mean, optoelectronic system. It is due to some facts. One of the important facts is related to the mechanical part, that in the traditional system, you know, mechanical systems or subsystems operate at low frequency. Low frequency means a lot of thermally excited photons can be entered to the system, and thermally excited photons means that we can easily lose the entanglement. Okay, let's start with this optoelectronic based quantum radar. The operation starts with the interaction of a high density laser with the optical parametric down converter material, and 2 photons, signal and idler, is created. They're entangled with each other. We keep the idler in the lab and use the signal, and this is our optical cavity, and the optical cavity output mode coupled to the photodetector. And in this idea, we use the quantum dot-based photodetector to enhance the sensitivity of the photodetector. So by coupling of the optical cavity to photodetector, a photocurrent is flow in the circuit, and by flowing the photocurrent here, a voltage drop across the varactor diode. This is the varactor diode we used in the system. By changing the optical current, which is a function of the coupling of the optical cavity with photodetector, voltage across the varactor diode is changed. By changing the voltage across the varactor diode, a depletion layer of the varactor diode will be changed. And change of the depletion layer varactor diode means the change of the capacitance induced by the varactor diode. So this is our microwave cavity. By change of the capacitor, LC resonator characteristic will be changed. Okay, we will try to use this optoelectronic system to generate the entanglement between microwave cavity mode and optical cavity mode. And this is our microwave cavity output modes. And before to propagate through the atmosphere, we need to intensify this signal, and we will use the, for example, transmitter. And by propagation of this modes, the intensified modes through the atmosphere, this is the atmosphere. In this idea, we used some beam splitters in series to model the atmosphere, and beam splitter operated as a scattering agent in this model. And moreover, the target scattering, this is the target model, and again we use the beam splitter to model the target, and CT is the backscattered modes of the target. Again, this backscattering signal should be propagated through the atmosphere, and then receiver and detector. Okay, let's start the model of the quantum. I mean, in this presentation, we specifically focus on the optoelectronic converter designing, and we, as you know, to design our system using the quantum theory, we normally start with the definition of the Hamiltonian. They are contributed to Hamiltonian for each system. This is our optical cavity, photodetector, and microwave cavity, and the Hamiltonian for the optical cavity and driving field, and Hamiltonian for photodetector, and the Hamiltonian for microwave cavity. And moreover, this two important Hamiltonian, which we will use this. I mean, this one's the interaction Hamiltonian to engineer the system to create the, for example, entanglement at high temperature, and the rate of interaction between the optical cavity and photodetector. And moreover, this is considered as the microwave cavity coupling to the photodetector, and EC for driving field, and E omega driving field for the microwave cavity, EC for the optical cavity, and considered as a strong field in this system. Okay, so here in this section, optical cavity and photodetector, and the rate of the optical cavity for define the rate of the optical cavity in this system, we use the first order perturbation theory, and moreover, to define the change and the interaction Hamiltonian between the optical cavity and photodetector, we use the dipole approximation method, and this is the result for the coupling of the optical cavity to the photodetector, omega c the frequency of the optical cavity, mu dipole moment, and the density of state of the photodetector, and Lorentzian function. And using this factor, which is the rate, you know, and times to the electron charge, one can easily calculate the photocurrent. And this is the photocurrent that we use to bias the varactor diode. I mean, by changing of this current, the varactor diode capacitance will be changed. And through this method, the optical cavity is coupled to the microwave cavity. And here we define the parameter as a mu c in the MC microwave cavity coupling to photodetector Hamiltonian, and it is related to the change of the capacitor in the system. Okay, so to analyze the system, we follow the procedure with the system dynamics equation of motion, AC using the Heisenberg-Langevin equation, AC for the optical cavity, C omega for the microwave cavity, and quadrature operator for the photodetector. I in, C in, and B in considered as a noise to the system. It is because our cavities, design cavity, interact with the environment. And moreover, kappa omega, kappa C, kappa omega, and gamma P considered as a decay rate for the cavities. And we need to linearize the system. It is due to these terms in the equation. To simplify the algebra, we need to linearize the system, and the linearization form illustrated here. And after that, we can calculate the entanglement between the modes, and more importantly, calculate the number of photons of the cavity. And for example, we have to calculate the number of photons of the microwave cavity. It is because after that, we need these photons, these signals, to propagate through the atmosphere to find the target. Okay, so before the propagation of this signal into the atmosphere, we need to intensify the signal, and we model the transmitter here using the beam splitter. This is the active medium, and called here active medium, to intensify the signal. And this is the microwave cavity output mode, and this is the output mode of the active medium. And here the expression that define this term, C omega. The first term stands for amplification of the signal. This is MC, or microwave cavity output, and this is the amplification factor. And the second term defines the noise effect, noise induced due to the active medium to the signal. And in the same way, we model the atmosphere using the beam splitter in series, and the first terms defined indicate the attenuation factor, the effect of the attenuation factor due to the atmosphere, propagation of the signal into the atmosphere. And the second term, it is the noise induced in the atmosphere. Okay, the results of our simulation or modeling. And here the graph A is for entanglement between the optical cavity and microwave cavity, and the graph B, optical cavity and the return field. This is return field for this. The distance between the transmitter and detector is around 2 meters, and with this specification for the atmosphere characterization and target, and moreover for the coupling between the microwave cavity coupling to the photo detector. And here it is shown that with increasing the temperature, the amount of the entanglement is decreased. And moreover, in this case, here it is shown that after 1 K or 1000 millikelvin, all of the photons become separable. Okay, we check here it is the symplectic eigenvalue that we use to evaluate the entanglement here, and here it is the formula that we used. And moreover, we check this result with other criteria, such as the entanglement metric, which as you know, we use the microwave cavity, optical cavity number of photon, microwave cavity number of photon, and moreover, it is the phase sensitivity between the optical cavity, phase sensitive correlation, cross correlation between the optical cavity and microwave cavity. And moreover, one can use this criterion, Simon-Peirce-Hordesky criterion, to check the result, and there is no problem with that. We calculate the entanglement with these 3 different methods. But here we replace the optoelectronic rather than the electro-optomechanic system. It is because we want to create the entanglement at higher temperature. It was the main aim of this idea. And by engineering, we found that by engineering the microwave cavity photodetector coupling factor, we can create, we can produce the entanglement at high temperature. But we know that this is just a theoretical simulation, and in the reality, generation of the entanglement as such, it is 5 Kelvin is I think it is impossible. And here the interaction between it is the rate that connect the microwave cavity to the photodetector. It depends on mu c, and mu c is a function of the optical current, and optical current is a function of the coupling between the optical cavity and photodetector, and we define the optical cavity coupling to the photodetector by this expression show, and GA omega p related to the GA OP. Okay, second part. In this part, I would like to discuss about our conceptual design of a quantum radar, and this is a start with the fact that we generate the I suppose that we generate the entangled photon here. The operation starts with the interaction of the laser with the OPDC, IIS and II as a optical entangled photon are generated. We use this signal and generate the C omega. This is C omega. C omega are entangled with IS. We calculated here, and the result illustrated here. And expectation value 2 eta shows that the 2 eta less than 1 means that the photons are entangled. So moreover, we calculate the number of photons of the microwave cavity, and here the number of photons for the microwave cavity, and less than 1 means that we have entanglement around, for example, the tuning frequency around 0. And moreover, the number of photons of the microwave cavity around 1 shows that our design quantum radar works based on the quantum illumination protocol that means that there is no problem with that. And so in the following, we need to calculate the power of the power generation by this number of photon. It is around -70 dB, and that means that our microwave cavity output power is around -1700 dB, and one can use this power to directly with no need to any transmitter to propagate through the atmosphere to detect the target. But we know that using this low power, all of the signal will be lost in the atmosphere. But so in the following, we need to use the, for example, transmitter in the system to amplify the signal, and this is the starting point for the simulation of the transmitter. In the transmitter, for transmitter and receiver, we use the ADS, Advanced Design System, and this is our MC system, microwave cavity system, works around 2 gigahertz. This is our signal, and this is around -1700 dB. And moreover, we generate this signal as an image of this signal, and we will use this signal in the receiver section to transfer our RF signal. This is considered as a RF radio frequency signal to the intermediate signal. Okay, so don't worry about this section, just focus on this part, 2 gigahertz with -1700 dB, and this is our transmitter. To design the transmitter, we use the ADS or Advanced Design System. The flow chart, the design flow chart in ADS illustrated here. It is a start from the schematic design in ADS, simulation in ADS, and PCB layout generation in ADS, and this is our final point, PCB layout simulation. Usually the PCB layout simulation result is different than the schematic. It is because in the PCB layout simulation, like reality, some factors such as the interference between the microstrip lines, and moreover, we know that microstrip line in a system can be operated as an antenna, and the PCB layout simulation considered the effect of the radiation and something like that. So, and this simulation needs to some optimization, and we call that co-simulation in the ADS, and this is called redesign. And when the PCB layout simulation results are satisfactory, we can order the PCB layout and implement the system. Okay, this is our transmitter design. Here we use some elements, electronic-based elements, bandpass filter, and moreover LNA. One of the critical difference between the quantum radar and the classical radar is the LNA that we use in the transmitter, quantum radar transmitter. Normally in a classical radar, we use the PA or power amplifier to amplify the signal, but we cannot use the power amplifier in the quantum radar system. It is because that the PA or power amplifier can induce a lot of noise to the system, and the noise can easily kill the entanglement. So we need to design low noise amplifier or ultra low noise amplifier. Okay, let's start with the bandpass filter. The PCB layout of the bandpass filter illustrated here. As you can see, there is no any lumped element in the system. All of the circuit designed with the distributed element port, input port and output port, and the characteristic of the bandpass filter. The red graph is for the reflection and the blue one for the transmission, and centralized around 2 gigahertz. And moreover, the other important factor is the noise figure. And noise figure for this design is around 0.2, which is very good point for the bandpass filter. And
5 minutes.
Yes, okay, no problem. And the other important case is the LNA, and for LNA, the PCB layout of the LNA illustrated here. This is the input matching network, output matching network, and we use the cascode transistor to intensify the signal, and the gain of the signal, the gain of the LNA illustrated here around the 2 gigahertz, 3 dB gain of the circuit, and the other specification of the LNA noise around 0.5. It can be considered as an ultra low noise amplifier, and moreover the reflection coefficient. And other factor for LNA that we have to consider is its linearity. And for linearity, you can consider this F as a central frequency 2 gigahertz, delta F equals to 1 megahertz. So F plus minus delta F gives us F1 and F2. And some frequencies such as F1 plus F2, F2 minus F1 can be easily filtered by the bandpass filter both. There are some frequencies such as 2F1 minus F2 or 2F2 minus F1 are the frequencies that we cannot easily filter. So we have to accept the effect of these frequencies. Both we define the intermodulation distortion, and in the design of the LNA, we use some technique to increase the IAM3 to increase the linearity of the LNA, and this is the comparison between the other factor. Okay, so this is output of the our transmitter. If you could remember, we start with this signal minus 700. After transmission, the transmitter output is around the level of the signal is reached around minus 68 dB, and the characteristic and the specification of the transmitter gain is around 80 dB, noise figure of the transmitter around 1 dB, and the reflection coefficient. Okay, come back to our original slide, and here the output of the transmitter reached to the other mode. You can also consider the other mode and our original mode, and minus 86 dB, and considering this target with RS 0.1 square meter, and using this equation, the range of the signal after this 2 meter and 2 meter here reach to minus 2200 dB, and this signal needs to amplification again, and this is the receiver that we used. The first part is designed as same as the transmitter section, but the second part relate to the IF signal, and I need to consider this. It is due to the fact that the frequency is different than the IF frequency. Here, the IF frequency, intermediate frequency, is considered as 0.6 gigahertz, and filter that we used here, it is the PCB layout of the filter and noise figure and the scattering parameter, and moreover LNA that we designed at 0.8 gigahertz. The noise figure of the LNA, you can consider that at 0.8 gigahertz, it is around 0.5 dB, and moreover this is the result for the gain is around 48 dB, and the stability factor and linearity of the receiver. And here, this is the input for the input signal for the receiver, minus 2200 dB at 2 gigahertz, and after amplification, it is reached to minus 100 dB, and this is the signal, IF signal. It is around 0.8 gigahertz, and after amplification, the level of the signal reached to minus 33 dB. Okay, so come back to our original slide, and so here after receiver, the level of signal reached to minus 33 dB. Okay, so here this is the signal that we use to make the cross correlation with the signal that we kept in lab, and by this signal, our signal to noise ratio for this system, for this conceptual design, reached to minus 20 dB. Okay, thanks for your attention, and we are so happy to be a part of COVID-5.
Thank you very much. Thank you.
You are welcome.
We have, maybe you already know them, some experimentalist colleagues, also engineers as well in our audience, and they already have some questions.
Okay.
We have a question from Bulat Rami from Gebze Technical University. Bulat Hoca asks, have you calculated the conversion efficiency of your optical to microwave converter concept?
So I think the question is about this part. Here, to calculate the optical cavity coupling to the photodetector, we use the first order perturbation theory, and moreover, H interaction, the Hamiltonian, the interaction Hamiltonian here, we defined, we use the dipole momentum to calculate the H interaction. So using the first order perturbation theory, we define the rate of coupling between the optical cavity to photodetector.
Okay. Thank you. We have another question. You can also read the question if you want from the chat box, but I will read for everybody.
I have to.
This is from
okay.
Yeah, Burak Alptu Yılmaz. He's from Aselsan. In transmitter and receiver parts, there can be lots of impedance mismatching matching problems.
Okay.
I see from your schematic sheet, all elements have chosen as ideal. Do you have their measurement results? Do you have chance to use their these two key parameters in your simulations? If you can read the question,
Yeah, I got the point. Okay, if you let me, I need to go to the transmitter and receiver section. Here it is. And if you let me in the transmitter, first of all, our simulation is not just in the schematic. All of them is PCB-based modeling. I mean momentum simulation. And here, if you could for LNA, I need to here in this section we use the input matching network. Input matching network to minimize the reflection from input, and moreover output matching network to minimize the output reflection. So using this in systems, I mean input matching network and output matching network in the system, we could minimize the reflection. And moreover, if you consider these results this one, and this is the simulation of all of this part, I mean transmitter, PCB-based transmitter, and the reflection coefficient for around the 2 gigahertz. You can consider this part, I mean, for input reflection, S11, it is around minus 15 dB, and for S22, I mean, the output reflection is below than the minus 20 dB. I mean, it is perfect for a transmitter to minimize the reflection. And the other question
there is about some bandwidth question. There is also at the end of the same.
This is and additionally, your bandwidth is very narrow. Is it actually, we need to choose a narrow bandwidth in quantum radar. It is because it is in contrast with the classical radar. In quantum radar, we need to choose the very narrow bandwidth. It is because by increasing the bandwidth of the system, you know, the signal to noise ratio will be decreased, will be strongly decreased. And moreover, by increasing the bandwidth of the system, for example, receiver, by increasing the bandwidth of the receiver, a lot of noise can be entered to the system. And moreover, from other point of view, when we increase the bandwidth of the receiver, the other signals, for example, you can consider the jammer, can easily jam our systems. Okay, so due to this fact, we have to consider the very narrow bandwidths for our system in quantum radar that you know the entanglement is very fragile, is a very fragile phenomenon and can be easily distorted by noises. Okay. Other question. is there any advantage for atmosphere propagation in using entanglement in frequency or polarization or time? We check the entanglement at each level of the quantum radar. If you let me, I need to show this part. Okay, so our results here. This, if you consider this part, it is the entanglement between the optical cavity, the graph B, display the entanglement between the optical cavity and the return field for 2 meter, I mean the propagation of the signal into the atmosphere for 2 meter. And theoretically, it is just theoretical results. And theoretically, we show that by changing the, using the optoelectronic signal, we can, optoelectronic converter, we can enhance the entanglement when we propagate the signal into the atmosphere. But I don't know if I correctly understand the question or not, but if it is not the right question, you can, repeat your question again, and I will try to answer to this question. Okay.
Thank you very much. There was one last part from the previous question, which is repeated about the range.
Range of our conceptual range is around 4 meter. 4 meter. We do our conceptual design for just 4 meter, but by increasing the range of the system, the signal to noise ratio, I think you know about, is a very important factor. And by increasing the range of the signal, radar system, this factor is strongly decreased. And due to this fact, we limited our design to very short range.
Okay, thank you.
Yeah, the second part compared to traditional radar, I think it is not comparable with traditional radar. I think you are talking about the classical radar. For a classical radar, here for example 2 meter, we just try to keep or save the signal to noise ratio, and moreover quantum correlation between the signal. So for this reason, we cannot compare our results with the classical radar that use for a classic correlation. We do the quantum correlation. We have to do the quantum correlation and preserve the quantum correlation.
Okay. Thank you very much. We thank Ahmet Salmanoğlu for this very nice, interesting presentation. Thank you very much.
I appreciate that. Thank you. Thank you so much.
You can close your screen share, and in the meantime, our next speaker can open. Oh, very nice picture. Okay. Our next speaker is Fatih Dinç from Stanford University, Applied Physics Department. He will explain us why quantum QED waveguides are non-Markovian. Okay, I will tell you that you have 2 minutes left at the 10th minute, okay? Then 3 more minutes for questions. Okay, thank you very much.
Thank you so much. Just a second. Yes, so thank you so much for giving me this opportunity to talk. I'm very honored to be here. Let me start by saying that what I will talk about today is actually an example of how to do applied theory. When people say applied physics, people tend to think about experiments. And there is actually a theory that you can do, and that's still inside applied physics, and this is one of them. And my interest in this topic is not necessarily from quantum computing, but rather in the idea of emerging concepts from many-body interactions. So what happens when we put qubits together, right? And I'm also warning you at this point, so I will be discussing qubits as a theoretical construct, but you can think of quantum dots, superconducting qubits, or MV centers as qubits. As long as something can be approximated as a qubit, we are fine. I took all the math away in this talk, so you need to provisionally trust me and you can check my math afterwards from the papers. And finally, why I have a Turkish flag here, it's because this is 23rd of April, and I wanted to honor that tradition where, you have a Turkish flag in TV today because it's, it's the sovereignty day of Turkey. Yes, awesome. So let me start with the acknowledgement. So what I'm discussing today is basically a reinterpretation of the results we got 1.5 years ago, together with my thesis advisor for my master's, Egi, who is now a researcher at IBM Quantum. And I would like to thank her because without her, none of this would have been possible. So you can actually just, after this talk, go ahead and look at this paper for the math that I will be discussing here. So let's start with the system model. So on the very high level, we have qubits, which are basically atoms with 2 levels. And then we have a bunch of them. And then they couple to an environment, which we, for the sake of simplicity, take to be a one-dimensional environment. And this is a waveguide for practical purposes. If you want to do an experiment of this, then this is a waveguide, right? And then these qubits, they actually have 2 states. So they have a ground state and an excited state. And then they have this resonant frequency. This frequency is the frequency of the pulse that you need to send to be able to excite this qubit, basically. And then they also have this decay rate, which is when you excite this qubit, how long it will take this qubit to decay, or in this case, inverse of the decay rate is that. So it's basically a time scale of the qubit's interaction, as well as it's also how strongly qubit interacts with incoming pulses as well. If it's a large value, then the qubit interacts with the pulses much strongly, but at the same time, if you excite it, it will decay much faster. And in this talk, we will be putting a bunch of the qubits together. They are going to be identical, and that's just for analytical convenience. We could look at non-identical qubits. And one important consequence here is there is no qubit-to-qubit interactions. All the interactions are going to be done via photons that are emitted from a single qubit to the waveguide, and then that gets scattered from another qubit and gets re-emitted and reabsorbed, etc., etc., etc. So there is no direct interaction, only mediated through photons. And there are 2 time scales. One of them is the level separation or the resonance frequency, which is basically a very short time scale or very high frequency scale. And the other one is the decay rates, which are longer time scales where the actual, the action happens, basically the time scale that we are interested in. And then they are also much lower frequency scales. So experimentally, omega is around gigahertz and gamma naught is around megahertz. And for the systems of our interest, omega is going to be much, much, much larger than gamma. So that means the pulse is basically interacting in a very narrow bandwidth. And if the distance between the qubits are much larger than the inverse decay rate, then we can think of them as isolated qubits. What does this mean? It means that the qubit, if the qubit is excited, it will decay and send out a photon completely before that photon interacts with another qubit. And if the qubits are close to each other, the exact opposite happens. So before the qubit has a chance to send off the full photon wave function, or the full photon wave packet, the photon will start interacting with another qubit and gets reflected, and then it will basically create an interference on its own emission. So this is basically the region where the collective interactions happens. The qubits start to become like a collective unity that has some interesting properties, and this is where the interesting collective many-body effects appear. And there is this approximation, which is basically the reason why I'm giving you this talk. It's called the Markov approximation. And the approximation's main idea is that if the distance between the qubits is very, very small, then you can neglect the time that it takes a photon to propagate from one qubit to another qubit. So this is the physical picture. It's a very simple picture. And the mathematical picture, and this is the only time that I will discuss mathematics here, the full theory has, so the time dynamics of the full theory boils down to a set of differential equations, which also include time delays. And Markov approximation takes out the time delay and basically replaces it with the current status of the field. And that's what it means mathematically to the Markov approximation. Why do we do this? Because it's easier. It's easier to solve the problem. It's basically possible to solve the problem because time delay differential equations are really hard to solve. On the other hand, ordinary differential equations are much, much easier to solve. So that's one part. So now let's talk about the decay rates. Right? We said the qubits, when they are very, very close to each other, when the distance is very small, they start interacting and then they become a collective unity that has basically decay rates. And this whole unity has a slow time decay rates. And if there are n qubits, there are n decay rates corresponding to n different modes of the superposition of those qubits. And then there are these non-Markovian decay rates, and there are infinitely many of them. And why do we call them non-Markovian? Because they are for events which are happening very fast, and due to the fact that the time propagation inside the system between the qubits is very fast. Or in other words, it's like, if it's not negligible, but very fast, basically. So when you do the Markov approximation, these decay rates become infinity because they happen instantaneously. And this is an example of what it looks like to calculate the decay rates. This is a complex plot. This is a complex plane. And then the roots of this complex, like this plot, or like the minimum values of this complex plots are the decay rates. And these 3 decay rates correspond to the 3 slow time decay rates of 3 qubit system. And then you also start seeing these non-Markovian decay rates. The y-axis is the real part of the decay rate, and the x-axis is the complex imaginary part of the decay rate. And you can see that non-Markovian decay rates are much bigger. So the processes are happening much faster. For the purpose of this talk, I will be discussing the slow time decay rates, because they are the interesting ones for us experimentally, because those are the processes that radiate outside to the qubit system. And we are looking at the outside of the qubit system, obviously. But again, I mean, we have like so this paper is like a 50-page long paper on the importance of decay rates and how to interpret them, yada yada. So if you really want to talk about all the properties of decay rates, there will be enough time. And then let's discuss the emergence of many-body or like many qubit effects. And for that, we will be looking at the decay rates. And remember, we are looking at those n small time decay rates. So for a system with n qubits, and under a very specific condition, that is called the Bragg mirror condition or superradiance condition. And it's actually, there are infinitely many of those conditions. n-1 of those decay rates become 0. What does this mean? It means that if you excite the qubits in a very specific way, in a very specific superposition, they will not decay outside of the system. The excitation will stay within the qubit system. Like one qubit will send the photon. So this is not really what's happening, right? This is just like me making a story of it. But basically the interference of the photons, the photon wave functions that are being emitted to the outside of the system will be destructive, and there will be no radiation out. And that's called the bound-staying continuum. And the one decay rate, which is like the one out of this n decays, and minus of them became 0, and the one of them becomes n gamma naught. What this means is all the n qubits, they come together and they create this one huge qubit, this one superqubit, which basically has a decay rate of all the qubits summed over. So it's a qubit that decays really fast. And this means that all the qubits are decaying collectively. So their decay is enhancing the decay of each other. And this is actually a Markovian effect. This is an effect that we see when we apply Markov approximation, and it's called decay superradiance. It's like from 1950s, 1960s. It's a very well-known effect. So what happens when we are relaxing the Markov approximation, also when we are taking into account the finite qubit propagation time within the system, is we are still seeing this n- decay rates going to 0, so they are still, the bound-staying continuum are still going to be there. But something weird happens to the decay superradiance. So think about it for a minute. You are separating the qubits from each other. So you would expect it would take a little bit more time for the qubits to decay. But what happens is the feedback of the photonic wave functions that are being emitted is aligned in such a way that the decay is actually increased. That's called superradiance, and that's the paper is all about. So basically, you get a decay rate which is stronger than the decay superradiance. And the reason why it's stronger is because of the positive enhancement effect coming from the quantum coherent feedback. So it's a full quantum effect. It's a full non-Markovian effect. You wouldn't have this in a Markov approximation because you are basically ignoring all those feedbacks in a Markov approximation. So this was the main idea of that paper. And now oh, by the way, before I move on, also, if you are interested in this topic, in this idea of superradiance, check this paper out. They were like the first people to come up with the concept. It's a very, very interesting concept.
2 minutes, Fadi.
Yeah, thank you. This is my final slide. But at the time, we didn't really realize something, which is that this superradiance happens at a very, so actually we realized this, but we didn't realize the meaning of this. This superradiance effect happens at a very specific critical distance between the qubits. which scales down as the qubit number increases. What does this mean? It means that even if you think L is negligible, you still have non-Markovian effects in the large qubit numbers, right? If you increase the qubit number, then you will still have non-Markovian effects, even though the distance between the qubits is small. And I'm going to do a back of the envelope calculation for you for like the parameters of Navaday experiments. And then this tells us that non-Markovian effects become non-negligible around 10 qubits. So if you are going to do any experiment that will include waveguides and qubits that are larger than 10, like qubit number that is larger than 10, then you can no longer do Markov approximation, which brings us to the topic, or the final slide, which is also the first slide of this talk, that waveguide QED is inherently non-Markovian. Thank you so much.
Thank you very much. So, are there any questions? You can ask through the chat box, but in the meantime, I can ask. There is already one ready. This is your conclusion is about non-Markovian behavior or Markovianity. This is just a matter of number of qubits, you say. I mean, what about the physical other constraints? Is it just a number?
I mean, there are other constraints. This is more like an upper bound. Let's say like this is like the best state of the art technology we have. But I think the more physical concept is that no matter what type of qubits we will use, and no matter how good those qubits, like the numbers will be, there will always be a number of qubits after which we will no longer be able to apply this approximation.
Mm-hmm.
I mean, 10 qubits is with current number, but the numbers will change, but the theory is always there. And the scaling of the critical distance scales with n to the -2, which means whatever the prefactor changes are, which depends on the numbers that you put in, there will always be like this problem that you run into in terms of theory.
Mm-hmm. Okay, thank you. There is a question from Özgür Hoca, Müstecaplıoğlu. You can also read if you want. Reading is more comfortable, but let me read it for everybody. Non-Markovian. Can you see the question?
Yes.
Superradiance, has been discussed in photonic crystals. Mm-hmm. Any relation? He asks, is there any relation?
Yeah. We actually discussed this with Dr. Müstecaplıoğlu before. That's actually a very good question. The difference here is we are not really changing the physics, right? The superradiance or the superradiance here comes from the fact that you are having this this interference effects between the qubits. So as far as I know, maybe I'm wrong, in these cases there's always something that's coming from outside, or you are either having a band effect, like the band, you're at the like near of the band gap, or like there's some other thing where the qubits are decaying to. So it's basically there's something else that's mediating this. Here it's completely the qubits and the fact that there is constructive interference. And as for the scaling here, the scaling here is with n, so it's a linear scaling. It's not a n-squared scaling.
Mm-hmm. There was a related question by Faruk Mirehvar about the scaling of super radiant case.
Yes, it's n. So it's with n. It's a linear scaling. It's just the prefactor gets increased with respect to the decay superradiance.
Mm-hmm.
Yes, I am seeing the question. Would you like me to?
Okay. And if it is, if your answer is complete for Mirehvar, then you can move to Ceyhun Hoca's question, Ceyhun Bulutay.
Shouldn't there be a characteristic time scale that should come together with number of qubits? Exactly. There is. And that's the thing, right? The time scale. Exactly. So the time scale that you can do, right? Which will come from omega and gamma naught, that will change the number of qubits that you can apply the Markov approximation to. But after that number of qubits, the Markov approximation will no longer be applicable. And in this case, there are some more constraints, right? There are constraints that gamma naught is much, much smaller than omega. And then there's also the constraint that omega times L should be comparable to pi. So these are things that I haven't discussed, but these should be there for you to be able to see these type of physics. And these constraints, so these constraints are basically what basically makes me say that 10 qubits is probably going to be one of the limits where we can do this.
Okay, thank you. Yeah, we are done. Any questions? I think we have no more. Okay, thank you very much. We thank Fatih Dinç for this very nice and also the last presentation of our meeting. So maybe we need to say a few closing remarks. My colleagues asked me to say a few things. I don't know why me. I am not the oldest. Maybe perhaps I am the boldest. So I will show a few slides. Let me first share my screen. Fatih says it is important to remember that SR scales.
I will just answer the question.
Okay, you can read. So I found this slide some time ago, before the conference, before this program, by Landau. We have some engineers. If any one of your mathematicians, if you don't know him, Landau was the greatest in former Soviet Union theoretical physicist. He was born in Baku, and it I think describes what we are living nowadays. And in some popular talks, I mentioned what happened a century ago between two world wars. People developed quantum mechanics today, which we are talking about its technological applications. So I think COBIT was a very nice meeting in the sense that in these very difficult days, we have been able to come together from many different parts of the world. In past, we never had such a great spectrum from, Hong Kong or States, Britain, India, and this was possible because of some colleagues. Some math, we had 22 talks, 12 recorded talks, and 8 posters. We thank all contributors, all speakers, presenters for this activity. And some special thanks. We have some organization group, but our local organizers, although we were not there physically, we needed some logistic and programming stuff. These 3 universities, Bilkent, METÜ, Middle East Technical, and Hacettepe universities are in Ankara. And here are the colleagues in these 3 universities who contributed most. And these green names are youngest colleagues. They were doing the real job. Mustafa Kahraman from Bilkent, he was the designer of this web page registrations, all these issues, and also including our logo or background. Zeki Seskir, we communicated through Zeki's channels in YouTube and in Zoom. And Nurdan from Hacettepe, she prepared our abstract booklet. Well, I started with Landau. Let's finish with Landau. There are only a few, English, documentaries that you can find about him. But this one is nearest to Turkish in Azerbaijan, or Azerbaijan Turkish, if you want. There is a theorem, they say, or nazariye by Landau. It is about hoşbetlik, which means happiness. Landau says that happiness is work, love, and communication. I think in COVID, this is what we have done. I hope that next time we will be in a much healthier and much comfortable conference. I hope to see you on COVID-6 next year, hopefully face to face. Okay, so thank you, and let me close this. Yeah. Teşekkürler herkese.